Alright, so here we are again for another session or another part of the lecture today for ENGR 2302 Engineering Dynamics. Today we're going to be, not today, but for this portion of the lecture we're going to be looking more at rotation and translation of rigid bodies or rigid body kinematics. So we're going to pick up right where we left off and work through some new material. Alright, so let us look at a representative slab or representative slice of a rotating rigid body. So this is a two-dimensional slice, essentially, of a rigid body. So let me double check this. Yep, we're good. Okay. Alright, so rotation about a fixed axis, representative slice. So rotation about a fixed axis. Representative slice. So I'm going to take that. Previously I was drawing a 3D object and it was very messy, but I'm going to break this down and look at just a horizontal slice, and that slice is going to be perpendicular to the axis of rotation. So let us say we have our x and y axis here, Let's see here, x and y, and I will again draw my potato, or my arbitrary rigid body. And I have a point O here, point O, and then I have a point P here, and that would have some vector r from the origin. And this point P would have to be, in the same plane as the xy axis in this particular case. So say I have vector r here, and then let me give this thing a velocity, as we've discussed previously. Where v equals omega k cross r. Omega k cross r. Omega times k cross r, or omega in this case would just be the magnitude. So here, and this plane again is cut. Plane is cut perpendicular to axis of rotation. And the velocity of any point P along the slice is v, as I've labeled on the diagram, omega cross r, omega vector cross r. So pay attention here, I had a omega just scalar here. So omega vector cross r, which is equal to omega scalar times k vector cross r vector. Omega scalar times k vector cross r vector here. Cross r vector. Or I could simply say that v equals r omega. If I were talking purely in terms of, let me label this as a scalar here. If I'm talking purely about magnitudes, this is what you learn in elementary physics class, in your high school physics, where you're not usually considering vectors. It's not usually a vector mechanics class. But in the scalar form, we can simply say v equals r omega. All right, so then I may create another, maybe I'll create another drawing showing acceleration. So I'll create another drawing showing our favorite potato. Here. X and Y. And then I have O. And O here. And then let us say I have two things. I'm going to have maybe a, just like I had a, let's say I had omega equals, omega vector equals omega k vector, and I have an acceleration, or an angular acceleration of alpha, and maybe I'll do this in green or something. Actually, I want to keep the P, I have the P in green, so let me get a different color. Maybe dark red. And then I would have alpha vector equals alpha scalar times vector k. And then at point P, I would have my actual acceleration vectors, and these would come in two flavors, or two components, I should probably say. I would have a tangential and a normal. A tangential and a normal, or centripetal. Let's see. So let us look at the acceleration here. Acceleration of any point P on the slab, or sorry, slice, of any point P. Well, I'm going to have A equals alpha cross R, plus omega cross omega, omega cross omega cross R, which will be equal to alpha k cross R, alpha k cross R, minus omega squared R. Omega squared R here. And then if I resolve into perpendicular and into tangential and normal components, I can get, actually let me do that on the next slide. I'm squeezing this down, so let me put that on the next slide. Just erase that here. Nope, I didn't need to get that. Omega squared R vector. And so then if I resolve the acceleration into tangential and normal components, what do I get? Well, I get that a tangential, AT, is equal to alpha k cross R, and then AN, and this will be in vector form, AN is equal to negative omega squared R vector. Or then in scalar form, I can say that AT is equal to R alpha, equals R alpha, and AN is equal to R omega squared. R omega squared. All right. Negative omega squared R. And again, why do I have a negative on there? Why does the normal vector have a negative on it? So why would the normal component have a negative, why would the normal vector, or the normal, the normal vector, the normal acceleration vector, have a negative component on it? The reason for it is quite simple. Oh, didn't mean to zoom in like that. Let me get out like that. Oh, what have I done? Okay. The reason for it is quite simple. You see, I can say that here, oh, interesting. Oh, let me play with this. Cool. Oh, I didn't know I could do that. Oh, cool. Okay. Playing with my tablet. Oh, let me just, okay. So here, the reason for this is if this thing is traveling in a circle, and there's the point P here, and we have a T and a N. If I can draw this, AN. Let's think about the radial vector, the vector R. What direction does that point? Well, if you remember, it points in the opposite direction, from the center, from the origin, to the point. So it is going to be in the opposite direction. It's not going to be equal and opposite. We're not talking forces here, but it is going to be pointing in the opposite direction of your radial component, or of your radial vector. All right. Okay, so let's continue here. So let us look at some more things, some more lovely material. Here. And don't worry, I promise we will work through a few examples. So let us look at the equations defining the rotation of a rigid body about a fixed axis. Of a rigid body. So these are your equations of kinematics, basically. And really, these are analogous to our linear equations of kinematics. About a fixed axis. About a fixed axis. So here, well, I can say the motion of a rigid body, rotating around a fixed axis is often specified by the type of angular acceleration. A fixed axis is often specified by the type of angular acceleration. So in other words, just as we classified, let me finish writing this, I guess, before I share that thought. Angular acceleration. So, just as when we were looking at translational motion, we would have uniform acceleration problems, we would have constant velocity problems, you would have non-uniform acceleration problems, and different sets of equations therein. We classify rotational motion in the same vein. So we're going to have the following relationships. Recall that omega is equal to d theta dt, d theta dt, d theta dt, or dt equals d theta omega, and that alpha is equal to d omega dt equals d squared theta over dt squared equals omega d omega d theta. So these are our basic derivative and other relationships. And so these are basically the tools that we're going to use to analyze various problems involving rotational systems, or about a fixed axis anyway. And when I say a fixed axis, I mean that the body itself is not moving through space, or can be considered at rest. So if you have a, one example of a problem would be uniform acceleration. Or sorry, not uniform acceleration, uniform rotation. Actually, let me do these on some later slides. So we have these basic equations, but then I don't have quite enough room, so I'm going to do this on the next slide. So I could look at, the simplest one would be the case where, well, the simplest one would be where the thing is just at rest, but we don't really worry about that type of problem. Why don't we worry about that type of problem? Why are we not going to worry about the case where rotation and translation are 0? Because this is dynamics class. Yes, this isn't statics class. Because this is dynamics class. Yes, wake up, everyone. Anyway, so if we have uniform rotation, where alpha is equal to 0, well, the equation will be fairly straightforward. So uniform rotation is where there is no angular acceleration. It's just going to be rotating at a constant rate. The Earth rotating about its axis would be a great example of this. Now we could talk on million-year timescales. The Moon is interacting tidally with the Earth and slowing down its rotation and blah 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 blah. But let's not worry about such things. We can just say the Earth is a uniform rotation problem, and we can treat it as such for most epochal time scales. So theta is equal to theta naught plus omega t. And then I could also, so that would really be your main equation of motion for a system of uniform rotation where alpha is equal to 0. And another special case would be you have uniform acceleration. In other words, alpha is equal to a constant. Our uniform acceleration rotation. So it is accelerating, but because the alpha is constant, things become much easier. Where alpha is equal to 0, or not 0, is equal to a constant, just some constant value. So omega would be equal to omega naught plus alpha t, where theta is equal to theta naught. In other words, the initial angular position. So theta naught here would be the initial angular position. This is the angular velocity and the time. Theta equals theta naught plus omega naught times t plus 1/2 alpha t. 1/2 alpha t. And omega squared equals omega naught squared plus 2 alpha times theta minus theta naught. Theta naught, or you could also call it, if you wanted to, you could also label this some sort of delta theta or something like that, the change in angular position. Oh, that's bad. You could also label this as a delta theta if you wished. So, do these seem familiar? Do these look familiar? Yes, and the reason is, and I'm going to make a little parallel between angular or fixed axis rotation and translational systems. So let us look at analogs. Analogs, translation versus rotation. Translation versus rotation. So let me write the equations that I just wrote. Omega equals omega naught plus alpha t. Theta equals theta naught plus omega naught times t plus 1/2 alpha t squared. And then omega squared equals omega naught squared plus 2 alpha times theta minus theta naught. These are the equations of constant alpha, of constant angular acceleration. And then we could have something like, if I wanted to compare it to the translational system, well, I would have something like V equals V naught plus AT, and I could then have X equals X naught plus V naught T plus 1/2 AT squared. This is the kind of equations we saw previously in our translational kinematics. And I could say V squared equals V naught squared plus 2A times X minus X naught. Do those look familiar? They should. We had this on the last exam. But anyway, although that was before spring break, so maybe your brain's melted in the sun over spring break or something. Who knows? These are the equations of constant translational acceleration. Constant translational acceleration. So we can see that there's a direct one-to-one correspondence here. And really that shouldn't surprise us, because all of these equations they really come from simple derivation, from simply taking, these are all built off of the idea that alpha equals some constant, or that A equals some constant. And then you're just taking the derivative of that repeatedly with respect, you're taking the integral of that repeatedly with respect to time, and that's where all these equations come from. That's where they're all from. So it shouldn't surprise us that all of these have very similar forms. And so from this, I can get the analog relationships. So they're not the same, but they are analogous in equations. So I can say that alpha is analogous to A. V is analogous. Actually, I should say omega is analogous to V, and that theta is analogous to X, delta X, whatever you want to say. And so we see that we have analogous relationships, and really the mathematics of translation are pretty much the same as the mathematics of rotational systems. At least when we're talking about a fixed axis. If we start dealing with masses and torques and forces and all of that fun stuff, we can get into more complicated things. Okay, let me work through an example problem. All right. So let's see this. Example. Now let us say, let's see, I have a pulley. With two different diameters. So I have an inner diameter here, which is a radius of 3 inches, which will have a radius of 3 inches, and this is going to be point A, and the inner radius will be 3 inches, and then I'll have an outer diameter of 5 inches. So A is the center of the pulley. Then I'll have an outer diameter of 5 inches, or sorry, outer radius, I shouldn't say diameter. If I can show you radius, that's a really bad circle. Looks like a fried egg. Okay, here's my perfect circle. If it doesn't appear to be a perfect circle, well, you see, you're looking at the board, and there, atmospheric effects. There's certain atmospheric lensing and little air currents that, light's very sensitive like that. It just looks like it's not a perfect circle. I swear to you that this was really a perfect circle when I drew it. It's just there's certain distortion in light, and it doesn't matter whether you're looking at it on the big board here or on your computer screen at home. That's just light distortion. That's all that is. It's not my poor art skills. That would, that's the logical explanation. Okay. So I'm going to have two cables here. One that's kind of like this, that comes in horizontally and wraps around and comes back the other way. And then I have 2 points, one vertical here at point D and one at C here. And then I have another cable that is wrapped around the pulley several times, or yes, let's just say it's wrapped around several times. Let me draw that in different color to make sure that we can be very clear that we're talking about two separate ropes here. This would be like, if I looked at it from, this is looking at it from the side. If I looked at it edge on, what I would see, if you can kind of get a feel for this in 3 dimensions, what this is looking like is something like this. It's a pulley of 2 different diameters like that, if I look at it edge on. And so we'll have our blue cable wrapped on it like this, and then I'll have a red cable wrapped around it several times, like this. And it's wound around the pulley in another perfect circle. Man, I gotta be careful with that light distortion. And then it comes down like here, and there is a weight B. There is a weight B. Some weight B. Okay. So all this is given. Oh, and this so I have to draw quite a bit for this example. It's a little bit complicated, but not too complicated that we can't solve it. 5 inches here. And then let us say we have a few other things. So all of this is given. And we also have a cable C has a constant acceleration of 9 inches per second squared. So what that means is it has a constant linear acceleration of 9 inches per second squared. How did I know that was a linear acceleration and not an angular acceleration? How did I know that? How did I know that it was when I say cable C has a constant acceleration of 9 inches per second squared? How do I know that's an A and not an alpha? Well, I mean, cable C, part of it will be rotating. It'll go around like that, right? So how do I know when I say 9 inches per second squared? How would I know that is linear and not rotation?
It says directness and right.
Well, that's true, but also what I'm really going to get at is the units. Something that is alpha is going to be either, I might call it radians per second squared, or just seconds to the -2 or something like that. Just nothing per second squared. The only real unit is the time unit. There is no distance in the alpha. And so also an initial velocity of 12 inches per second, both to the right. But yes, to the right would also indicate that it's a linear acceleration. Both to the right. And then I want to find, and so notice this is, again, kinematics. I'm not going to tell us anything about the forces, the masses, the torques, the momentum, moment of inertia, none of that stuff. We'll get there. That'll come in later chapters. But right now we're looking just at kinematics. We're only going to describe, I'm just outright telling you, this is the velocity, this is the rotation. Then let us consider how these things carry through. So determine A, the number of rotations of pulley in 2 seconds. In 2 seconds. B, the velocity and change in position of point B, of load B. And this is, if you can't tell, this is hanging from this. Load B, again after 2 seconds. After 2 seconds. And C, the acceleration at point D, at t equals 0 seconds. At t equals 0 seconds. At t equals 0 seconds. All right, any questions about the setup so far? All right. Okay, so let's work through all of that lovely nonsense. Okay. So let's, again, the first thing we're going to be looking for is the rotation, number of rotations in 2 seconds, or the number of revolutions, we might say, etc. Okay, so the first thing I'm going to say is that the tangential, let's definitely keep that. Sorry about that. Okay, so solution here. Well, the tangential velocity of, and the acceleration of d, tangential velocity and acceleration at d of d, which is the point on the pulley, are equal to the acceleration and velocity of c. So I'm going to say initial here. So I'm going to write Vd initial, Vd naught equals Vc naught equals 12 inches per second to the right. So the velocity of d initial equals the velocity of c initial equals 12 inches to the second to the right. And then I can also say that Vd naught is equal to r omega naught, and then omega naught is equal to Vd naught, my d's look like o's occasionally, d naught, Vd naught, velocity at d initial. And then I can say omega naught is equal to Vd naught over r is going to be equal to 12 over 3 equals 4 radians per second. So that is our initial angular velocity of point D, which is actually a part of the pulley. And then AD, the acceleration of D, let's see, at t, at any time t, is equal to AC, which is equal to 9 inches per second squared to the right. 9 inches per second squared to the right. And then AD at some time t equals R alpha. And then alpha equals AD at some time t over R, which is equal to 9 over 3, which equals 3 radians per second squared. 3 rads per second squared. And the reason I'm using this at time t, because the acceleration is going to be constant. It's the velocity that will not be constant. That's why I'm looking initially at the not condition here. Okay, so I have the initial angular velocity of point D here, and I have the angular acceleration. And I will just apply some more equations to this. I want to apply, and on the next slide, I'm going to apply the relations for uniformly accelerated rotation to determine the velocity and angular position of the pulley after 2 seconds. So omega here is equal to omega naught, so just basically our rotational kinematics equations for constant acceleration. Omega is equal to omega naught plus alpha t, fairly simple plug and chug, equals 4 radians per second. 4 radians per second plus 3 radians per second squared times 2 seconds times 2 seconds equals 10 radians per second. 10 radians per second. And then theta is equal to omega naught t plus 1/2 alpha t squared. 1/2 alpha t squared equals 4 radians per second. 4 radians per second times 2 seconds equals 1/2 times 3 rads per second squared times 2 seconds quantity squared. And all of this will equal 14 radians. Okay, so that is going to be the number of, that's the change in angle between up to 2 seconds. And then n, let n be the number of rotations or revolutions. And n equals 14 radians times 1 rev over 2 pi radians, equals the number of revolutions. And so doing that simple multiplication, I can get that n is equal to 2.23 revolutions, and this was one of our desired quantities. 2.23 revolutions, and then VB is equal to R omega equals 5 inches times 10 radians per second. Times 10 radians per second, which will be 50, which will lead to that VB equals 50 inches per second upward, or 50 inches per second upward. And again, velocity B is, point B is here. Now let me get rid of that little, I can't, so I wish I hadn't drawn that little arrow, so let me just, I'll fix it. It's just a big candle of material, big block. There we go. Let's just say it's a great big block B. Problem solved. I guess I was being a little sloppy there, just showing that it was an arrow connecting it like a vector, but I don't know if I would necessarily like that, because I want to make sure that it's not necessarily moving downward. If this thing is moving to the right, then this thing is twisting like this, which means that we're raising the weight. 50 inches per second upward. 50 inches per second upward. And then I can also get some other things. Then I can say the delta y at B, the change in position, is simply going to be equal to r times theta. In other words, it's the change in arc length along the outer radius of the pulley. That makes sense, assuming there's no slipping. It's going to be 5 inches times 14 radians times 14 radians is equal to, finally, delta yb is equal to 70 inches. Delta yb is equal to 70 inches here. And now I want to get the accelerations for part C here. So next, I want to evaluate or break apart or resolve the initial tangential and normal acceleration components of D, tangential and normal acceleration components of D, acceleration components of D, all right, so alpha d at any time t is equal to AC, so which is just 9 inches, 9 inches to the second, 9 inches per second to the right, and that's the tangential. Sorry, I shouldn't say a time t. I should just say it tangential, and then AD normal. I guess I was saying time t. Sorry, that's a little bit of an error on my part. I shouldn't be saying time t for the subscript t. That is the tangential, not the time label. So AD then, in the normal direction, would be equal to RD omega naught squared equals 3 inches times 4 radians per second squared. 4 radians per second squared equals 48 inches per second squared. 48 inches per second squared. And then the components, AD tangential is equal to 9 inches per second squared. 9 inches per second squared, and that would be to the right. And then AD normal would actually be pointing downward or toward the center of the circle, and that's 48 inches per second squared. 48 inches per second squared downward. Okay? And so then if I want to combine these into a final acceleration, overall acceleration vector, well, I would have maybe the acceleration at d, and then I would have the normal components, or actually the tangential in this direction if I want to be consistent. This would be the tangential AT and AN if this is the center of the circle, and then AN here, the normal component. And so the magnitude of AD, and let's call this phi here, phi between here. AD is going to be just our Pythagorean, and that's n squared AD n squared plus t squared. And then that is equal to the square root of 9 squared plus 48 squared. And we get a magnitude of 48.8 inches per second squared. And then the phi is just going to be equal to the inverse tangent of simply 48 over 9. And I get that phi is equal to 79.4 degrees. 79.4 degrees. So I could define my overall acceleration either as a set of tangential or normal components, or I could describe it as a magnitude and a direction, like you always can. Okay. All right. Questions on that? Okay. So quite a bit. That's my brief example on rotation about a single point. So now we need to move on to something a little bit more tricky, or a little bit trickier, and that is general plane motion. General plane motion. Not as complicated as the three-dimensional motion, but it is still a little more complicated. That's not right. Okay. Anyway, after I finish this one, I'm going to pass this around and just look at the first slide and then just see what is wrong with this picture. But anyway, anyway, it's kind of humorous. So analyzing general plane motion is quite funny. Analyzing general plane motion, or just general plane motion. consider general plane motion. So when I am talking about general plane motion, what do I mean by this? What do you think general plane motion is? Well, it's quite simple. General plane motion is the flight path of a military aircraft carrying a high-ranking officer. I'm so sorry. Get it? General plane motion.
I was going to ask about private plane motion.
Okay. Yeah, is there a private plane motion as well? Okay. Anyway, we are very serious people here. Anyway, so what general plane motion is, previously we have talked about translation and rotation about a fixed axis. And that word fixed was a crucial sort of gotcha word. That was a very crucial power word, or that was an SAT word or something. So that was a very critical word, a key word. And so, so in other words, we were saying that we either had translation or we had rotation. Something is either flying through space and translating and not rotating, or it's rotating but it's not translating. In general plane motion, we have a combination of both translation and rotation. So that's what I mean. That's what we mean when we say general motion. In other words, it has nothing to do with the Admiralty, and has everything to do with the fact that we're talking a general case, like general, like you probably heard special versus general relativity. We're talking general. We're talking a generic. In other words, it describes. We start getting closer to describing the motion of real objects, where they have both translation and rotation. So. And when we say plane motion, what we mean is two-dimensional. So we're not looking at a z-axis, or we're looking at just an x and y, or just an x and a z, whatever you want to define it. So, in other words, it is rotating and translating in the same direction. So, or in other words, I could state it is that the vector for the object's rotation will be perpendicular to the translational path of the object. So, in other words, we would have if I draw this out, say you have a object that initially is here, and let's say we have the center initially A1, and maybe up here it's originally, and then maybe I have B1 up here, and then at some time later I'm going to have, so this would be for a wheel or something like that. Well, A2 is still at the center, it's the center of the circle, but now B2 is all the way at some other, it's going to be at some other angle. It's going to be somewhere down here, B2. And so maybe initially I would trace my vectors here, like this, but then it's down here like this. So we have a combination of both translation and rotation. If we had pure translation, this thing would just be sort of skidding along the ground. It wouldn't be rotating at all. It would just be like a block along the ground. If it was only rotating, well then this thing would just be, this axis would just be in a support, like a bracket or something, and it wouldn't be allowed to translate. It would just be rotating about an axis. And so it's a combination of translation with A, plus rotation about A. Let me show that. Rotation about A. Rotation about A. Here. And so here, if we had just the translational case where this was sort of skidding along the ground, where you had A1, A2, and this thing just kind of skids along the ground. And B1, B2, and then we add to this the rotation if it was just about a fixed point. If this thing was just sort of glued down or pinned down, is more likely. And so you had B1 and then B2 down here. It's a combination of translation and rotation. Okay, so again, we're combining translation and rotation. But if I look at, again, so if I were to define the, what is this, I want you to sort of make sense of this sentence here. Again, when I talk about the vector for rotation, I am talking about the vector of its axis of rotation. So this thing is going in a path, but if I look at the vector for its rotation, well, if I use my right-hand rule, the axis would actually have to point into the page, wouldn't it? The axis would, if I apply the right-hand rule like this, I suppose, the vector for the rotation would have to point into the page. And so from there, I can see that the vector for the rotation is actually perpendicular to the path of rotation, or sorry, perpendicular to the path of translation. And that's just as we described previously. All right, so again, general plane motion is neither translation nor rotation. Is neither translation nor rotation, nor rotation, but a combination, but a summation of the two. How many? But a summation of the two. Of the two. Actually, you know what? Let's have some fun. There, that's some nice alliteration going. General plane motion is neither translation nor rotation, but the summation of the combination. Got it? I could say two, but I probably should just say two there, but I wanted to have a little more alliteration in my combinations of summations and translations and rotations. Anyway, so if I draw a general shape out again, that was for a simple circular object, a disk. But what if I show this here? So I'm going to draw a potato again, maybe draw this out a different manner. Now I can't draw this perfectly, so I'm just going to kind of illustrate that my potato is shifted a bit. If I could do this very perfectly, I would copy this and paste it over here, but we won't, so that's okay. Let's say we are, let me label some points, A1, A2, A1, A2, and then B1 and B2, and B2, B squared, B2, and then maybe B1 prime. B1 prime. So if things were purely translating, well, this is going to be, this is both translating about, this is both, the shape is both translating and rotating about A. So this shape is both translating and rotating about A. So I could say then, if this thing were just translating, I would have, if it were only translating, B would end up at point B1 prime. So again, these would be parallel lines. If this were only translating, so let me define B1 prime. The point B would be at if body was only translating. Only translating. And then I will also have a rotation. I'm also going to have a rotation from a rotation that instead of having just a translation, I also have a rotation about A, and that's what makes me go from B1 prime to B2. So the body actually rotates a bit as such. And so we can say that the displacement of all particles can be divided into two pieces, or parts, can be divided into two parts. The translation of A2 and B1 prime, sorry, not of, to A2 and B1 prime, and the translation, or sorry, the rotation of B1 prime about A2 to B2. About A2 to B2, but not R2D2. That was a Star Wars reference. Anyway, I have the most lovely humor in this class. I'm thinking about starting up as a stand-up comic. Just, just try it, yeah. If this whole teaching thing doesn't work out, what my plan is I'm just going to get a whiteboard, one of those rolling whiteboards, and just sort of roll it onto the train downtown, and I'm just going to be like busking but teaching. So just dynamics all day long, up and down the train. Oh, sorry, yes. So rotation of B1 prime about A2 to B2. Okay. Anyway, I also then need to look at absolute and relative velocity in plane motion. Here. Oh, so next topic, absolute and relative velocity in plane motion. What do these mean? Absolute and relative velocity in plane motion. In plane motion. Well, let's see here. Here. Basically, the idea is any arbitrary or any plane motion. So I think I'll write this out and then I'll draw it. Can be replaced by translation of an arbitrary point or arbitrary reference point A, reference point A, and a simultaneous rotation about point A. About point A. And a simultaneous rotation about point A. So if I have two absolute velocities here, let's see. let's say I have I'm going to draw my sort of potato body again. And I'll draw this potato 3 times. Oh, I don't want to do it in that. I want to do it. I like making my potatoes in purple. Where did that go? Oh no, did I lose that? Uh-oh. Shoot. Let me see something. We'll keep that. I think I may have accidentally erased that. I hate it when that happens. Okay. Well, I didn't lose too much, I don't believe. No. Okay, so let me do that again really quick. So we'll start that again. Any plane motion can be replaced by a translation of an arbitrary point of an arbitrary point A, arbitrary reference point A, reference point A, and simultaneous rotation about point A. About point A. About point A. So if I draw my potato again, I'm going to try to draw the same potato 3 times. So I'll draw something like this. Looks kind of like a kidney bean or something. That looks really bad. Something kind of like that. And I'm going to say plane motion, translation with A, so plus plane motion or equals plus plane motion translation with A rotation about A. If you remember transforming things into a force couple system from statics, this should look a little familiar. Remember how you can transform forces, move them to different, you can say if you have a force on a body, you can find an equivalent force couple system about a certain point if you wish, and it looks fairly simpler. So say you have points A and B, and all of them here. So A and B, 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 and the velocities here. I would have VA. So initially, let's say I have VA and VB here. And these are just arbitrary velocities. These are global velocities. These are in the global coordinate system. And I could say that these could be talking about, this would be equivalent to both of these moving with VA, translating, and VA here. And then this thing not moving, but then a velocity that is v of b with respect to a, b with respect to a, and then a rotation about here. So an omega, or omega k. And this would be fixed, omega k. So if this thing were fixed and this were just a combination of rotating and a relative velocity there. Okay? Questions on that? So just a basic conceptual question, or conceptual topic. So here, I could again say that VB, working through some equations here for this system, is equal to VA plus V of B with respect to A, V of B with respect to A, and then V of B with respect to A is equal to omega K crossed into R from B to A, or from R A to B, B with respect to A. And therefore, V of B with respect to A is equal to R omega, and then VB is equal to VA is equal to VA plus omega K. Omega K, I like to use my cats for my unit vectors, crossed R from B to A. And just some general equations there. Okay? Let's consider another system here, how we might describe this. Maybe let's look at an example of how this might work. Okay? Any questions on that basic idea? Okay. Okay, so here, let us say we have a system that consists of two sliders, basically. So I'm going to have a system like this, and this is just basically two sliders with pins. So let's say I have a sliding, let me draw this in maybe two different colors. Maybe put this one a little bit over here. To make clear, this is a long longitudinal track. And here, there is a sliding block here. It cannot move in the horizontal direction, but it can move in the vertical direction. And then there is another one that can move horizontally but not vertically. I have a horizontal track that can move horizontally but not vertically. And so I have two blocks and tracks. Two blocks and tracks, and let's say they're connected to each is a pin. And let us look at this here, and there will be a rod connecting the two of them, connecting each of them here. And the velocities here, well, I'm going to call this point A, and this point B. And VB will be pointing downward. VB will be pointing downward. And VA will be going to the right. So I'm saying this thing is moving to the right, and the only way this thing can move to the right is if point B moves downward. This is a rigid body. The rod is a rigid body. It cannot stretch or compress. So the only way for A to move to the right is for B to move downward. Well, and this would be if I look at the rod itself, this would be an example of plane motion. Why? Because it's going to be translating, center of mass is going to be moving downward, for instance, and to the right, but it's also going to be rotating. So it's going to equal, let's say we could look at it from in terms of A, translating with A, translating with A, plus rotating about A. Rotation about A. Oh, and also I will define an angle theta. That will be important. Angle theta will be the angle, well, this is the center line of the bar. this is going to be theta here, from the vertical to the bar here, the center line of the bar. Oh, and also this thing will have a constant length of L. Constant length of L. All right, so when I say translation with respect to A, what I mean, of course, is that we have something like this. So imagine both parts are moving, both A and B are moving with VA, and B is also moving at VA. And then I could have another system here where I'm rotating about A. Where I am rotating about A. About A here. And so this would be, I would have, B would be moving, it would have both a relative velocity, V of B with respect to A, and also I would have some omega. Omega treating A as fixed, as a fixed rotation. And if I could define all of these, I would say that V, velocity V, or VB, is equal to VA plus VB slash A. And so I would have a relationship like this. Just a simple vector summation relationship. Something like this, where VA maybe is to the right, and VB slash A is downward like this, and VB is downward, is perfectly downward, so this is a right triangle. And B slash A, velocity of B with respect to A, is the hypotenuse of that triangle. All right, questions like that, or questions on that? Okay, so continuing on, I do have some notes on this that I want to cover. Some more on the system, and this will be, I think, the final item for today. I'm just finishing up some notes on this particular system, analyzing how it would all work together. Quite a bit on this system, actually. So, all right. So, assuming the velocity, assuming that the velocity VA of end A is known, let's say we wish to determine the velocity B, the VB of end B, and the angular velocity omega. The angular velocity omega so all of that stuff previously was the given, essentially, and this is what we want to find. And the angular velocity omega in terms of VA, so I guess this is really our first example here, L and phi, or sorry, theta. I've got to be consistent here. So the direction of VA and VB are known. They're horizontal and vertical, or I guess vertical and horizontally, respectively. Direction of VB and VA are known. And so let's say I want to complete the velocity diagram, which we have already. Complete the velocity diagram. And that was just the triangle we had previously. So I know that VB over VA VB over VA is going to be equal to tan theta, and then VB is equal to VA tan theta is equal to VA tan theta, and VA, and also VA over VB with respect to A is equal to VA over L omega over L omega is equal to the cosine of theta. And then omega is equal to VA over L cosine theta. Over L cosine theta. L cosine theta. So we already have that. Let's see. Let's look at this here. There. If I go and look at this from a different direction, or a different perspective, what if I flip the perspective here? What if I flip the perspective? Use B as our reference point. Well, in that case, we end up with something very similar. The bar will now be equivalent to, or bar's motion will now be equivalent to, let's see, so it'll be equivalent to the summation of, now everything would be moving with respect to B, or we would say that A and B are both translating with VB plus a rotation about point B. These essentially are equivalent. What we described previously and what we have now are equivalent. So I would have VB, and then plus a rotation about B. So I can look at this from either direction. I can look at this from either perspective, and it will turn out the same, and we can actually use that to solve for a few things if we wish. So this would be B, assuming a fixed rotation. And then we would have an omega about B and a velocity v of A with respect to B. And in this case, our velocity triangle would look like this. We would have VA, I would have VB, and then going the other way this time, V of A with respect to B. A with respect to B. So again, let me go through this. Selecting B as a reference point. And solving for velocity VA of end A, and angular and omega, and angular velocity omega leads to the equivalent velocity triangle shown here. Velocity triangle. And then some other notes. VA with respect to B has same magnitude but opposite direction, which is not surprising. Magnitude but opposite direction. of V BA, of B with respect to A. So the sense, the direction again, the sense of the, or the direction of the relative velocity depends on your choice of reference point. However, the angular rotation is independent. The angular rotation, angular velocity, so again, what direction the relative motion is pointing will depend on what reference point you choose. However, the rotation doesn't. This thing only has one rotational velocity. So the angular rotation, rotational velocity omega, will not depend on your reference point. It will not depend on the reference point. All right, and then, because angular velocity is independent of reference point, and then assuming the velocity v, let's say we say that assuming let's see here, and we could do the same thing, same kind of calculation we did previously, solving for VB, etc. Okay, and that really is what I wanted to cover. So just a few notes on that. All right, so I do have an example problem that I might work through starting on Thursday, but I think that a numerical example that we might work through on Thursday. But I think this is going to be the first of 3 days covering the general motion of rigid bodies. All right, that'll do it for today. Thank you for watching, and as always, thank you.